In this problem, we're given a grid and we're given a point where we started and a point that we have to reach. And we want to find the fastest way to go from the start till the end. There are walls which add signs, and the twist on this problem is that in one stroke, we can move between 1 and k squares in either north, south, east, or west. So what that means is, for example, if we have, let's say, k equals 2, so we can move at most 2 steps in one move, and we start here, and then 1, 2, 3, and we end here. So starting here, we can go 2 steps. So in one move, we can go either here or here, and let's say we go here, and that means in the next move we can go here, or we can go here. So that means to reach from the start to the end, it'll take at most 2 steps. So we can go here, which take 1 step to go here, and the next step will reach here. So our answer here will be 2. So how do you tackle this problem? First thing first, we read in the height, the width, and our k value, and then we have a grid. So we can just create a vector of strings called S, and then for I we can just cn si, and this is to be of size h. Okay, so this is our grid now. So first thing first, we gotta know where we start at. I missed it. We read that in before. So we have to have an int of start x, start y, and x and y, x, x, y, tx, ty. So this is where we start and we end. And let's zero index everything to make everything a lot easier. Minus minus y, minus minus tx, and minus minus ty. Okay, so now everything is zero indexed. So the first thing we'll do is we'll create a matrix called distance, which will keep track of the fastest way to reach any square from our starting square. So it'll have dimensions h and w because we zero indexed everything. And then rather than mem set it, just put it out. Oh, actually, not as this mem set it. Mem set this to 0 size of. Actually, still what if in the minimum way we have mem set everything to infinity, and then we ensure that our starting distance is 0, because to get from the starting square from itself, you don't need to move anywhere, so it's a square of 0. So now we'll have to keep track of where we've been, and using Dijkstra's algorithm we can just do that using a queue. We'll have a queue of pair int int. So in the pair, the first value will be the score to get to the cell, and then the next one will be the cell x coordinate, and similarly this would be the cell y coordinate. Yeah, so I think that's our queue. And initially we start at our starting cell, so we would just insert a score of 0 and sx sy, and like Dijkstra's, so while q dot size is bigger than 0, we continue. So yeah, so the first thing we're going to do is we take the top of the queue out. So we do so it'll be a pair int. I'll call top q dot front, and then I pop it so from the queue. So we take the top from the queue, and now we travel north, south, east, and west. So that will be for I04, and we can just create something called dx of size 4 which is we can travel in the x direction either minus 1, 1, 0, 0, and similarly we can travel in the y direction minus 1 or 1. And if you look at them as a pair, in the 0th index, that means we would travel minus 1 in the x and 0 in the y, so we'd be traveling to the left. This means we're traveling to the right, this means we're going down, and this means we're going up. Okay, and then we go in each direction, and we'll also go from 1 to k plus 1. So first thing first, we're to see if we can reach the squares in the current direction. So our new x would be the same as our top dot second dot first. So that'll be our x plus dx times I, and our new y would be top dot second dot second plus dyi. We're going to times this by k. So sorry, by j here. So that'll be our new x and our new y. So if it's an at, so if an x and y equal to an at, it's a wall. So that means we can't travel anymore in that direction, so we just break from this. That makes sense. If the distance of nx and y is less than, let's create a cost variable. So our new cost would be the same as the cost to reach to the cell we're on plus 1. So if the new cell we're looking at already has a lower cost, then there's no point continuing, because to reach, if you look at the next cell in front of it, we can use the lower cost, which is already there. So there's no point in continuing. However, if it's the opposite, such that our new cost is a lot better, what we can do is we can say, okay, now let's change this value to new cost, because that's the smallest number of moves we can to get to the cell, and then let's add the cell back into the queue. So we insert new cost, and x and y. We keep on doing that, and then hopefully by the very end, if we mem set it to infinity, if I'm not wrong, we did. So if dist of tx ty equal to infinity, we then output minus 1, minus 1, minus 1, else we output dist of tx ty. And let's see. Okay, need an extra one here. It's not insert, it's a queue, not a set. It's my special for loop. Q dot. I didn't make it into this itself. It has to be a parent int. Okay, and now let's see if that clears up all the bugs. So our first value of this should be 5. And we crash horribly. Put 0 as y while size is bigger than 0. Q dot front, I pop the front off with the Q. We travel in each of the directions. And the current one is at we break. But what if we, okay, there's an issue that if when we add k we go out of bounds, then that's where this issue comes from. So if the new x is less than 0, or the new y is less than 0, or the new x is greater than or equivalent to the height, or the new y is greater than or equivalent to the width, then we just break. 0. Yo, that should be enough. Okay, that's enough. And the answer is 5, which I believe we do get, but our C out is just in the wrong position. Okay, one last time we just do F, paste this, we get 5, good. Next we paste this, we get 2, good. Next we paste this, we get -1, perfect. This looks good to me. And voila.